Okay, let's practice writing some reactions totally. So looking at what reactants we are putting together, one or more, looking at what type of reaction we're dealing with, and then using that to predict what kind of products we're going to make, how our atoms are going to rearrange themselves. As long as we know the reaction type, we should be able to predict what our products are going to be and how our atoms should rearrange. So let's look at this first example. Tricarbon octahydride and elemental oxygen react to form two new chemical compounds. Okay, well, tricarbon octahydride has some hints for us in what the formula is. So tri is 3, so I have 3 carbons. Octa is 8, so I have 8 hydrogens here. Okay, so that's my tricarbon octahydride reactant. Let's see, what about my elemental oxygen? Well, elemental just means the element on its own, so just O. But be careful, oxygen is one of the 7 naturally forming diatomic elements. So it's not going to be happy just on its own. It's going to pair up with itself to make O2. Okay. The other diatomic elements like hydrogen and fluorine and bromine, iodine, nitrogen, and chlorine can be remembered by Hofbrinkel. Okay, where each one of these is a diatomic, H2, O2, F2, Br2, I2, N2, Cl2. So if I ever have just an elemental form of chlorine or nitrogen or iodine, it's not just going to be Cl or N or I, it's going to be Cl2 or N2 or I2. So these are my two reactants I'm putting together in this reaction. All right, so just based on these reactants, I should be able to figure out what reaction type this is. Well, it kind of looks like a single replacement because I've got carbon and hydrogen hanging out together. I've got this elemental oxygen, so I'm putting together a compound with an element. But this is a little more specific. I have carbons and hydrogens reacting with O2. This is a combustion reaction. I'm going to be burning this stuff. Okay, so what I'm going to make on the other side is just going to be carbon dioxide and water. Okay, combustion is the most strict about how we make our products. I could have C3H8, I could have CH4, I could have C4H10, I could have C2H2. Does not matter. As long as I have C's and H's reacting with O2, my products are always going to be CO2 and H2O, no matter what. Okay, now to write that out and balance it is another thing. But to get the products, it's always going to be CO2 and H2O for a combustion reaction. So they can be tricky to balance, but they're the easiest to predict the products for because you don't even have to like try and rearrange the atoms and say what pairs up with what. You are going to get CO2 and H2O if this is a combustion reaction, and this is. Let me write that off to the side. Let me do it. I'll do it in orange. This is combustion. All right. Put a little plus to show these are two separate products. Okay, and then I can balance this. So I'll do this kind of greenish blue, I guess. Well, no, let's do orange since we had orange for the combustion thing over there. So let's balance this. Let's start with carbon. So I've got 3 carbons on the left. I've got 1 carbon on the right. So let's get 3 carbons here by making a coefficient of 3, so that multiplies to this carbon. And that's also going to affect our oxygens, but we can deal with that later. So we fixed our carbons. See, we have 8 hydrogens on the left. We have only 2 on the right. So if I put a 4 there, 4 times the 2 H's that are already there, make 8. So that fixes my H's, which is good. Also affects my O's. So now that I've got my C's fixed, I've got my H's fixed, let's try and figure out the O's. So on the left or on the right side, let's look at this first. I have 3 times the 2 O's that are here, so that makes 6 O's. I've got 4 times the 1 here, so that's 4 more. So in total on the right side, I have 6 and 4. I've got 10. I have 10 O's here on the right side. Okay, so how do I get 10 O's on the left side? Well, I don't just put a 10 here because that would be 10 times as many O's as I have here. It'd be like 20 O's. So if I want something times this O2 to make 10, if I had a coefficient of 5 O2s is a total of 10 O's. I don't have to touch my C3H8. It's already good to go, so I'm going to drop a 1 in there. So 1 C3H8 plus 5 O2s should be able to make 3 CO2s and 4 H2Os. Nice. So just from the reactants in words, we can figure out the entire balanced reaction equation, which is crazy. It's awesome. Okay, let's look at another. Mercury 2 oxide reacts and breaks down into the elements that make it up. Okay, well, this is a pretty big giveaway here, that we have just one thing, Mercury 2 oxide, okay, and it's breaking down into its elements. Okay, so the giveaway here is that there is no other reactant to react with. We're not rearranging atoms with something. We're just breaking this thing down into all the stuff it's made of. So if I can figure out what the reactant is, I can just split it up into those different elements that make it up. So mercury 2 oxide is going to be, well, I got Hg and I've got O. Now be careful. Remember this Roman numeral 2 right here is not so you can be like, H2, okay? That is there to tell us the charge. And a lot of times it gives us the opposite answer than putting the 2 here. So if I had a positive 2 charge on this mercury, and my oxygen has a negative 2 charge, well, a positive 2 and a negative 2 cancel out as is. So it's actually good to go just like that. HgO is mercury 2 oxide. Okay, so be careful with that Roman numeral. Make sure you're canceling the charge, not just sticking that number somewhere and hoping for the best. Okay, so HgO is our only reactant here. It's going to break down into the elements that make it up. So I should be breaking this apart into my mercury as an element and my oxygen as an element. Okay, and then I have to ask myself, are either of these pure elements going to be one of those Hofbrinkel guys? Well, Hg is not, so I can just leave that as Hg. It's monatomic. But my O is definitely part of Hofbrinkel. This is going to be a diatomic, so it's going to be O2 instead of just O. All right. Oops. So now we've got kind of the basis of the reaction equation. HgO is going to break down into Hg and O2. Now we just have to balance it. Okay, well, I have one Hg on both sides, so that's good. I don't have to touch that. I have 2 O's on the right, only 1 on the left. So if I put a 2 here as my multiplier, 2 HgOs means I'm going to have 2 O's to match what's on the right, which is good. But that also means I'm messing up my Hg's. But that's okay. I fixed my O's. Now it's time to fix my Hg's. I have 2 Hg's on the left. Time to get 2 Hg's on the right. So I've got 2 Hg's, 2 Hg's, 2 O's, 2 O's. Anything that's left blank, I can just throw a 1 in because we are done. We are balanced. Okay, so 2 HgOs can break down into 2 Hg's and 1 O2 in this decomposition reaction. I'm just going to write decomp because I'm kind of running out of room there. This is a decomposition reaction. Okay, one thing is just going to break up into multiple stuff. Okay, let's look at this next one. This time I'm going to try not to forget to say the reaction type before we start just writing it all out. I start going into autopilot. Okay, elemental zinc and hydrogen monochloride react to form 2 new chemical compounds. Okay, well, elemental zinc, let's do red for this guy. Actually, let's do pink. So elemental zinc is just going to be Zn. Now that Roman numeral 2 is going to tell me the charge it's going to have in a compound, but on its own I can just leave it as is. So this is still just going to be zinc, and that Roman numeral 2 is going to come in handy in a bit here. Okay, hydrogen monochloride tells me with the prefixes what I should have. So I've got, come on, here we go. Hydrogen is just H. If I had 2 hydrogens, it would be dihydrogen. If I had 3, it would be trihydrogen. But in this case, I don't have anything there. It's just because the mono prefix doesn't get used on the first element. So this is like monohydrogen. It's just hydrogen there. And then monochloride means I have 1 chlorine with this. So 1 Cl here. Okay, so what's this going to be? Well, I have 1 pure element and I have 1 compound. So this is going to be a single replacement. This time it's not a bunch of C's and H's reacting with O2, so it's not a combustion reaction. This is a, let's see if I can fit this in here, single replacement. Here we go. I'm actually going to move this over a little bit. Oh no, I grabbed the whole thing. There we go, that's a little better. Okay. This is a single replacement reaction. So what that means is one single thing is going to bump its way into this compound and kick something out in the process. Okay? So my pure element is what's going to be doing the kicking. It's going to kind of force its way into this compound, and something else has to go away. Something else has to leave this compound, either the H or the Cl. Okay? Now how do I figure out how to do that? Well, all I have to do is look at which things have a similar charge. I can't put zinc into this, which is going to have a positive 2 charge, and expect it to just suddenly become negative and satisfy something else that's going to be positive. I want my charges to cancel. So if I'm going to be putting my zinc with something, I want to replace a positive thing, since this is going to end up having a positive 2 charge. So out of these 2 things, hydrogen or chlorine, hydrogen typically has a positive 1 charge and chlorine typically has a negative 1 charge based on our little shortcut from the periodic table. So if I'm going to swap it out for something, I'm going to swap it out for the positive thing. All right, so I'm going to bump the hydrogen out. It's going to go away. So on the other side here, I'm going to be making zinc paired up with the chlorine. Okay, now this is an ionic compound. It's a metal and a nonmetal, so I have to make sure my charges cancel. Well, what kind of charge does my zinc have in this case? That's a positive 2. I'm putting a 2 plus up here, just so I don't forget that. Chlorine should have a negative 1 charge, just by looking at the periodic table. So 1 chlorine is not going to be enough. If I had 2 chlorines, I could have 2 negative charges to cancel out with this positive 2 charge. That would make this compound happy. So it's not just going to be ZnCl, it's going to be ZnCl2. Okay, now that's one product of my reaction. The other thing is going to be the element I kicked out just hanging out on its own. So now hydrogen is all by its lonesome off of the side here. Now I have to check if it's a pure element. Is this one of the Hofbrinkel guys? Is this one of the naturally diatomic elements? And hydrogen is. It's the H in Hofbrinkel. So this is not going to be just H. It's going to be H2. Whew, okay, that was a lot. Okay, but now that we have all the right chemical formulas, we can balance this. So let's see. I have 1 zinc on the left, 1 zinc on the right. Cool, not going to touch that. I have 1 hydrogen on the left, 2 hydrogens on the right. So if I want to get 2 H's on the left to match these 2 H's, I could put a 2 here, and I'm going to erase this little pink arrow to show that we're bumping hydrogen out of the way. Maybe I'll put it down below. That way it's kind of out of there. Cool. Okay, if I put a 2 here, my coefficient means I've got 2 HCl's, so 2 H's and 2 Cl's. Okay, so now I've got the 2 H's to match. Let's see. Oh, hey, haha. Now I have two CLs on the left to also match the two CLs I have on the right. So that kind of solved two problems at once. That's kind of great. Two birds with one stone. So I have one ZN on both sides, two H's on both sides, and two CLs on both sides of the arrow. Everything is balanced. I don't lose any atoms or come up short. This is a balanced reaction equation. So just by saying I'm bringing together elemental zinc and hydrogen monochloride, we can predict what we're going to make based on the reaction type. And then we just balance it once we have all the right chemical formulas in the right places. Let's look at a couple more examples. All right, elemental iron and elemental oxygen react to form one new chemical compound. Okay, so let's write this out. So kind of like in the previous example, we have an element that has that Roman numeral. On its own, it's not going to mean anything. So this is iron, but I'm not going to be like iron 3. Okay, that's not right. This 3, this Roman numeral 3, means I'm going to have a positive charge when it's together in a compound. As it's an element, it doesn't really do anything for me right now, but it will come in handy later. So for now, this is just iron. It's not one of the diatomics. There's not like triatomic iron out there or something. Okay, I'm reacting with elemental oxygen, which, hey, I'm starting to get used to this. Oxygen is one of those diatomics. It's going to start coming up a lot. So when oxygen is on its own, it's not just going to be O, it's going to be O2. Okay, I guess that's something else I should clarify. That doesn't mean that it's always going to be O2 in whatever compound it makes. Like you'll notice in HGO up here, we didn't have HGO2 because like, oh, oxygen is diatomic. It's only a diatomic when it has nothing else to bind with it to make a compound with. So don't just start putting O2s everywhere. Make sure you check canceling or check prefixes first to see how your formula works out. But if you have elemental oxygen or anything else in Hofbrinkel, that's when it becomes a diatomic. Okay, so if I'm putting together Fe and O2, these are two elements. I have elemental iron and elemental oxygen. Even though this is a diatomic, it's still an element. There's no compound here. So if I'm putting two simple elements together, this is a synthesis reaction. Synthesis. Synthesis. There we go. Okay. In a synthesis reaction, I basically just shove everything together. Everything just gets piled into one compound. All right? I just have to make sure that I cancel out the charges correctly to get it. So my Fe is just going to combine with my O2 to synthesize a single product. Everything's getting shoved into one chemical. Okay? So that's kind of the key thing about synthesis is you get one product. So Fe plus O2. Okay, this is an easy mistake to make. It's not just going to be, oh, I'm just going to put Fe and O2. Like it's all there. Okay, that would make sense, kind of at a glance. But if we check the charges on this, this is not going to work out. Fe should have a charge of positive 3 based on this Roman numeral right there. Roman numeral 3. Oxygen, let's see, on the periodic table has a negative 2 charge, and we have 2 of them. So that's going to be a negative 2 and negative 2. So we can't cancel positive 3 with negative 4. That would leave a negative charge left over. This is not going to be a happy compound. So that's not really going to work. Okay, so how can we put together our iron and our oxygen in a way that cancels out our charges? Well, if I just have my one iron and one oxygen, I have too much positive charge. If I had two oxygens, I would have too much negative charge. So it looks like I'm going to have at least one other iron in here. Okay, because otherwise I can't hit that nice balance between canceling out all the positives with the negatives. So let's put two irons in here. See what happens. So we've got a positive 3 and a positive 3. So total, that makes positive 6 charge on our iron. So how many oxygens do I need to cancel out a positive 6 charge? And that's a question mark. It's kind of a bad question mark, but there we go. How many oxygens do I need to cancel out a total of positive 6 charge? Well, if each oxygen is a -2 charge. If I had 3 of them, that would be -2, -2, -2. That would be a -6 charge. All right, so let's do that. If I had 3 oxygens here, all that positive charge from the iron is going to cancel with all that negative charge from the oxygen. I'll have nothing left over. So my compound is Fe2O3. This is my chemical formula for my product. Okay, so we have combined the Fe and O2 into one happy ionic compound. Now we just have to make sure that all our atoms are showing up in the reactants and the products. So let's see here. Well, I have only one Fe on the left and 2 on the right. So let's fix that first. I'm going to put 2 Fe's here so I can match the 2 Fe's on the right. Let's see. I've got 2 O's on the left, 3 O's on the right. Okay, well, I can't really say like 1.5 O2s. That doesn't make any sense. So if I get stuck in a place like this where I have kind of a weird odd number that won't work itself out, I'm just going to double everything that I have and see if I can fix it from there. So this 2 is going to get doubled to become a 4. This blank spot would be like a 1. I'm going to double that to a 2. I'm going to double this to a 2, and then see how that works out for me. Okay, so now, let's see. And now I doubled everything. Let's see if I've solved my odd number problem. I have 4 Fe's here. 2 times these 2 Fe's is going to be 4 Fe's. So that matches. That's good. 4 Fe's on both sides. All right. I've got 2 O2's over here. So that's a total of 4 O's on the left side. On the right side, I have 2 times 3 O's. So that's going to be 6 O's on the right side. So if I have 6 on the right and only 4 on the left, I don't have enough. So let's try this again now that we have kind of solved the odd number problem. Okay, well, what can I put here to match the 6 O's on the left side? If I already have 2 here, if I put a coefficient of 3, 3 times the 2 O's I have there gives me 6 O's to match the 6 O's over here. So hey, that looks balanced to me. 4 Fe's can react with 3 O2's to make 2 Fe2O3's in this synthesis reaction. All right, let's look at one more example. Barium nitrate and magnesium sulfate react to form 2 new chemical compounds. Okay, so this is going to get a little rough because this has polyatomic ions in it. But do not freak out. As long as you can remember to keep your polyatomic ions together as one thing, do not go divvying them up into other elements. You will be fine. So let's look at our barium nitrate first. So barium is Ba. Nitrate is a polyatomic ion. That is NO3. And the whole thing has a negative charge. All right. My barium on the periodic table has a positive 2 charge. All right. So if I want this to cancel out to make a happy compound, positive 2 and negative 1 is not enough. I would need to have this nitrate, this NO3 thing with the negative 1 charge. I would need that there twice. So this whole thing is going to be there twice. So I put parentheses around it, put a little 2 down there to say the whole NO3 thing is there twice. That means I've got 2 of those little negative charges to cancel with this positive 2 charge. So that is now canceled out and happy. That's my barium nitrate. Let's see what our other reactant is going to be. So this other guy is magnesium sulfate. So magnesium is Mg. Okay, and on the periodic table, it has a positive 2 charge, just like barium. It's in the same column even. Sulfate is another polyatomic ion. It's sulfur with a bunch of oxygens, just like how nitrate is nitrogen with a bunch of oxygens. So sulfate is going to be SO4. It has a negative 2 charge overall. Well, okay. If I've got positive 2 and a negative 2 canceling out, I mean, that cancels as is. I don't have to have any more Mgs or SO4s to make this work. So I can just kind of leave that. All right. So MgSO4 is fine to leave there as a formula. It's good to go. That's kind of nice. So my barium nitrate is this formula here. My magnesium sulfate is this guy here. Now I just have to get them to react to form two new chemical compounds. In order to figure out those products, I have to know their reaction type. So what do I have here? I have two compounds here. I have a compound made of a positive thing and a negative thing, a compound here with a positive thing and a negative thing. So if I want this to react and change somehow, this is going to be a double replacement. Let's see if I can squeeze this in here. Double replacement. Okay, this is going to be kind of a tight fit, so I think I'm going to move this down a little bit. Oh, I missed the plus and the arrow. There we go. Okay, now it'll give me a little bit more room. Okay, so in a double replacement, we take two compounds and switch either their cations, the positive ones, or their anions, the negative ones. Okay, we're basically doing a square dance. We're doing a swap of our ions. So it's kind of like a single replacement, but with a happier ending. Instead of with some element out on its own, we're going to have everything still coupled up with something else. They're just kind of switching partners. All right. So if our barium comes first, it's our positive thing, and our magnesium comes first, it's our positive thing there. These guys are going to switch. So my barium is going to go take magnesium spot, and magnesium is going to go take barium spot. Okay, now you can also switch the negatives. So you can switch the nitrate over here and the sulfate over there. Just make sure you don't do both at the same time, because then you're just going to end up with the same compounds. You're going to switch the barium to the right and the nitrate to the right, and then it's just going to be barium nitrate again. So just pick one or the other. I like to switch the positive ones, just because I like to stay positive, and then leave the negative ones. But you can also move the negative ones. That's fine too. Works the same way. Okay, so in our double replacement, we're going to put our magnesium in the place of our barium. It's going to be paired up with, my nitrate here. And remember, just like before, we have to make sure that these cancel out charges. Kind of like with the ZnCl2. I can't just like be like, oh, we had one before, so it should still be fine to have one Cl. I have to actually look at what my charges are going to cancel out in this new compound. Okay, sometimes it's not going to be the same kind of formula setup as it was before. So in this guy here, magnesium has a positive 2 charge, like I said before. And nitrate has a negative 1. So this is actually going to look pretty similar to the barium nitrate, since barium and magnesium have the same charge. They act similarly in a chemical reaction. So my nitrate thing, that whole thing, the NO3, has to be there twice in order to have two negative 1 charges to cancel out with our positive 2 charge. All right, so we're going to have MgNO3 as one of our products. Now, what about the other thing we make? Okay, well now our barium is going to be in the spot of the magnesium, and it's going to be paired up with sulfate. Barium has a positive 2 charge. Sulfate has a negative 2 charge. So if I take a positive 2 and a negative 2, those cancel. They're fine as is. So I can leave those alone. So it's just going to be BaSO4. Okay. So on my product side, I'm switching a pair of my ions, either the positives or the negatives, and replacing them with each other. So I get these two compounds. Okay, and now all I have to do is balance. All right, so let's see. BaNO3 2. Let's do barium first. I have one barium on the left side, one barium on the right side. Okay, well, that's good. So I don't have to change that. What about nitrate? I have two NO3s on the left side. I have two NO3s on the right side. So hey, that's good too. So that's fine. I don't have to touch those. There's one Mg on the left side, one Mg on the right side. Okay, that's good. That's fine. And then one SO4 on the left side and one SO4 on the right side. That's also fine. So I don't have to fix anything. This is already balanced. You will find that a lot of double replacement reactions are pretty easy to balance because it's just a switching of ions, and it all just depends on the charges. So a lot of times you either come up with a bunch of ones across the board, or maybe there'll be some twos and maybe some threes, but a lot of double replacement reactions tend to be a little bit easier to balance, which is nice. Okay, now it's not always going to be this easy, okay, and you're not always going to get formulas that are so easy to balance. So always make sure, always check to make sure your charges are canceling if you're making an ionic compound. If you're not having prefixes to tell you the way, make sure you check your charges cancel. Okay, have a periodic table handy. So this is our balanced double replacement reaction. 1 BaNO3 2 can react with 1 MgSO4 to form 1 MgNO3 2 and 1 BaSO4. So look at that. Just with knowing the words of what reactions we're trying to put together, we can figure out what our chemical reaction is going to look like, which is crazy. Okay, for stuff at the atomic level that we can't really see atom by atom, we can predict how things are going to work with these 5 fundamental reaction types. Now, if you're having trouble with this, it takes practice, like everything in chemistry, in which, some people are going to get tired of me saying it, but you got to try and you got to practice it in order to get better at it. And it will get easier the more you do it. So if this is tough for you, stick with it. Look for the patterns, okay? Figure out what reaction type you have and use that basic form of the reaction type to figure out how your atoms are going to rearrange or combine or break apart from each other.